So this is a recitation on the project that we are going to do for CE 182, which is on preliminary analysis of a sand and gravel pit conversion to a water reservoir. If you recall, we did a couple of homeworks. The first was just understanding this concept that in places such as in Colorado, where the water is scarce and expensive, oftentimes such pits that are mined for sand and gravel um, are converted into water reservoirs. And we also learned about slurry walls, which is one of the techniques that is used to contain the water, because sand and gravel is quite permeable. So we would want to hold the water in place and not let it leak. So oftentimes slurry walls are used. So let's start with the project description. Our project site is in Greenstown, Colorado, where we have a sand and gravel pit that's about 3,000 feet in diameter and 20 feet deep depression in the ground. So if you look at the gravel pit, on an average, it is about 3,000 square feet, 3,000 feet in diameter. And then if you look at any cross section and draw it, then we have a long 3,000 feet or so. So 20 feet or so in depth, and these slopes are 2.5 horizontal to 1 vertical. That they have to maintain in order to maintain the slope stability. And then the idea is that if we, so the second paragraph says the value of water in Greenstown is approximately $10,000 per acre foot. So that's how typically the value of water is expressed. So if you have an area of 1 acre and it has a water that's 1 foot thick, then the volume is 1 acre times 1 foot, and that much water holds a value of $10,000 in Greenstown, Colorado. So if we hold water in this reservoir, okay, the total volume, the area is about 160 acres. If you convert 3,000 feet in diameter to the area times 20 feet in depth, the value of water is about 32 million. So it is worth storing the water and using it for the town of Greenstown. So the owner is considering two alternatives. So what it's saying is that the elevation at the top of the ground surface is 60-40 feet above the mean sea level. Okay? So they have a borehole log somewhere on the site, okay, and we have that available for our preliminary analysis. So the elevation at the top of the ground here is 60-40, and then the borehole log goes down to 5 feet, 10 feet, 15 feet, 20 feet, 25 feet or so when it stops. And let's zoom it in and see. The description is widely graded sand with gravel, widely graded sand with gravel, widely graded sand, and so on. And the sand, gravelly sand, stops at about 20.5 feet, and below that it is all claystone. So claystone is a type of soft rock which starts almost here. It's a soft rock with very low permeability. So alternative 1 says that the owner is considering raising the reservoir capacity by building a ring concrete dam around the pit that is 18 feet high, gaining additional 15 feet of storage. So, based on the borehole log, we can assume that the bottom of the pit is at elevation 60-20, since the top of the ground surface was at elevation 60-40, and we know from the borehole log that it is about 20 feet deep. So for all practical purposes, we can assume that below this it's impermeable. So we have initially 20 feet of water, and if we raise that capacity by another 15 feet, then the total height of water will become 35 from elevation 60-20 to elevation 60-55. The concrete dam is going to be 4 feet deep. If you see that the elevation of the ground surface is 60-40 and the bottom of the concrete dam is 60-36, and the dam starts 8 feet from the top of the excavation. So the design criteria it's telling us is that the maximum exit gradient needs to be 0.3. So you can imagine that the water is going to flow from here underneath the dam, and when it appears on the other side, when we have this dam, let's say, okay, and 4 feet of soil, right? When the water comes up, the exit gradient needs to be less than 0.3. Okay? And then it also says that the minimum factor of safety of 1.5 against uplift. So what's going to happen is that below the dam, we are going to have water pressure, and if the dam is too light, this force from below, which is called uplift pressure or uplift force, will make the dam float essentially. So we have to make sure that the structure is heavy enough. So if the weight of the structure is W and the total uplift force is U, we want to make sure that the factor of safety, which is W divided by U, is greater than 1.5. Okay, so when you design, build your model in SIPW, you can find pressure heads at many points below your dam, and then integrate them over the length of the dam to find the total uplift force. So the idea here is to design the cross section of the dam to meet these requirements and consider additional elements such as cutoff wall as needed. So this dam starts at 8 feet from the top of the slope, and it's going to be 4 feet deep. So those two dimensions are fixed. So you can change the length of the dam and make it shorter or longer, or you could also consider adding cutoff walls, right? So that the water goes around it and reduces the exit gradient if it's greater than 0.3. So then it goes to the cost. A lump sum construction cost for the concrete dam is expected to be $7 per cubic foot of concrete. So you have to calculate that after your design is done, how much volume of concrete it's going to take the dam around the entire length of the reservoir. And in addition, it says it's $19 per square foot of sheet pile cutoff if needed. So if you add a cutoff, then the cost to construct that is also given. Okay. In addition to that, the you are going to lose water to seepage underneath the dam, right? So we have to consider, we have to calculate that amount of water and do it per year. And you know that the value of water is $10,000 per square foot. So you can convert that into whatever amount it comes per year. The second alternative is to build an embankment using available clay from a nearby site and supplement it with a slurry wall. So the idea here is to keep on building on top of the ground an embankment using a nearby clay and adding a slurry wall. Slurry walls are typically 3 feet wide. The slopes of the clay embankment must be 2.5 to 1, just continuing this slope here. So the same slope is the embankment upstream as well as downstream. And the elevation of water is the same. So the total height of water is 35 feet. Once again, we can also assume the ground surface to be or the clay stone here to be impermeable, and the design criteria that's given is the maximum exit gradient not to exceed 0.3. So first you would consider just the embankment without the slurry wall and see how the water is, what is the exit gradient. And the second thing you are going to do is start, if the exit gradient is not less than 0.3, then you will start adding slurry wall at some increments until your exit gradient here is less than 0.3. So you may not need the slurry wall to go all the way into the claystone, or you may. So you will find that out after you do your analysis and cost estimates. So in this particular case, the cost is told that the lump sum construction cost of the earth dam is expected to be $1.5 per cubic foot. So you would have to calculate this volume going all the way along the perimeter of the reservoir, and then multiplied by $1.5 per cubic feet or cubic foot. And then the cost of slurry wall construction is given as $9 per foot depth and per foot of length. So what it means is that the thickness of the slurry wall doesn't matter. So it's so if you look at the slurry wall, if it is 1 foot deep, okay, whatever its thickness might be, if it's 1 foot deep and in the direction perpendicular to the paper, if it's 1 feet deep, then this much volume is going to cost $9. Okay. Similarly, for the previous alternative one, for the sheet pile cutoff wall, for 1 foot deep versus 1 foot into the piece of paper, that area was going to cost $19. So you can add that. And in addition to that, we can consider the water loss depending on how deep the slurry wall is and its permeability. And then you have to consider the loss of water in your cost analysis, again per year. So we have been given some data. We already talked about a borehole log that was given to us. Using that, you can estimate the type of soil you are dealing with, and then use these two empirical numbers for hydraulic conductivity for the native sand and gravelly soil, and pick an appropriate value of permeability or hydraulic conductivity using these two tables. Okay, so you are going to use these tables to estimate hydraulic conductivity or coefficient of permeability for native soil. Okay. Then it is given that the permeability of a compacted clay of the proposed embankment. Okay, so permeability of the compacted clay of the proposed embankment is estimated to have horizontal permeability of 10 to negative 5 centimeter per second and 10 to negative 6 centimeter per second in vertical direction. So when embankments are built using compacted material in layers, you sometimes you expect to see higher permeability in horizontal direction than vertical direction. So what it is saying that the permeability in horizontal direction, KH, is 10 to negative 5 centimeter per second, and in vertical direction it is 10 to negative 6 centimeter per second. So just remember and be careful in converting these values into meter per second, because you will set up your model in meters. Or if you set it up in feet, you have to convert this in feet per second. And then the permeability of a slurry wall is estimated to be uniform and 10 to negative 7 centimeter per second. So if you are adding a slurry wall, it's given a uniform permeability of 10 to negative 7 centimeter per second. Your task is to perform preliminary analysis of both alternatives and make your recommendations based on cost and sustainability. Okay. And sustainability, you will account for economic impacts, and you have been given economics related to the construction and water loss. And then there are obviously social impacts and other things that you could consider. Deliverables, there are 2 deliverables for this project. So you are going to do it in a team of 2 people. So the first deliverable is due in the week of April 27th, where you are going to provide us a brief memorandum describing the permeability you selected for the native soil. So you have only 2 tasks. And the second, that you have to provide preliminary CPW models for both alternatives, including boundary conditions, because we want to make sure that you are setting up your models correctly. And then your second deliverable is due on May 7th, which is a full technical memorandum describing the project objectives, all the way to conclusions and recommendations. And we have, so that's your second deliverable. And we have provided you templates for both deliverables. First template is just our usual memorandum. The names of the 2 of you are going to be here. We have already given you the subject. You put the date, and you start with an opening paragraph that's 2 to 4 sentences, and go on to then write down the title, project description, and objectives the way it's shown, and then describe the project in your own words. Then talk about how you interpreted the subsurface conditions and came up with the hydraulic conductivity for the native soil, and give your table of all parameters that you are going to use. And then you are going to also present the 2 CW models. So the final deliverable is due for everyone or all teams on the same day, which is May 7th. So this is going to be May 7, 2020. And the subject is already given. And you take your first deliverable and keep on modifying it. So here you still have an opening paragraph. Then you have already described your project in your own words. You can update it based on the feedback we provide after your first deliverable. Then you should have also completed second part. And in the third part, it's going to be long, and you are going to describe all your models, all your analysis, and then conclude and say which alternative you are going to recommend, and what additional information is needed to finalize the analysis. So, and then you attach as many tables, figures, attachments, references that are needed. There is no page limit, but of course, be concise as usual, and the usual formatting requirements where the titles need to go above the tables, and for figures, the titles are below them. Cite all the tables and figures in the text, no significant or no unnecessary significant digits, good quality graphics, good looking tables, and all those things are still expected.